All right, let's take a look at Chapter 12, Introducing Probability. In Chapter 12, we cover the idea of probability, the search for randomness, probability models, probability rules, finite and discrete probability models, continuous probability models, random variables, and personal probability. The idea of probability. Chance behavior is unpredictable in the short run, but has a regular and predictable pattern in the long run. Randomness and probability. We call a phenomenon random if individual outcomes are uncertain, but there is nonetheless a regular distribution of outcomes in a large number of repetitions. The probability of any outcome of a random phenomena is the proportion of times the outcome would occur in a very long series of repetition. So here we have an example of flipping coin, right? The proportion of times that you get a heads should be about 50, right? But you can see by the x-axis that if you flip one coin, then maybe you don't get a heads at all, right? If you flip two coins, it looks like they got one heads and one tails. They flipped three coins, they didn't get as many heads as they got tails because we're below the axis. And all the way up until 10 tosses, it looks like we're tossing more tails than we are heads. Once they start tossing 13, right, they have the highest probability of heads possible. They start, though, if you look at the second graph here, that in the long run, right? So the first graph, you get up to like 20 coin flips. In the second graph, we have 500 coin flips, right? And it looks like around the 250 coin flip area, or maybe even the 100, it starts to really get to a 50-50 chance, right? So there's a 0.5% chance that you have a heads, or the proportion of times that you flip a heads is 0.5, 50% of the time. Search for randomness. Computer programs including applets, random number tables, physical means such as tossing coins or rolling dice, and the chaos theory. And quantum mechanics. So we find random numbers by looking in the random number table, right? But you could also toss coins or roll a dice, right? So who's going to start the game? Let's flip a coin and decide. So we consider that a random way of choosing. And then you also see the idea of randomness in chaos theory and in quantum mechanics. Probability models. Descriptions of chance behavior contain two parts: a list of possible outcomes and a probability for each outcome. Probability models. The sample space S of a random phenomenon is the set of all possible outcomes. An event is an outcome or a set of outcomes of a random phenomenon. That is, an event is a subset of the sample space. A probability model is a mathematical description of a random phenomenon consisting of two parts: a sample space S and a way of assigning probabilities to the event. Here's an example. Give a probability model for the chance process of rolling two fair six-sided dice, one that's red and one that's green. So we have here a chart where you can see down each column the red dice being rolled: a 1, a 2, a 3, a 4, a 5, or a 6. And across each row, you can see the green dice being rolled: a 1, a 2, a 3, a 4, a 5, or a 6. so that we have all 36 possible outcomes. Our sample space, it has 36 outcomes. We have the 1, 1, 2, 1, a 1, 2, right? And on until we get to the 6, 6. Since the dice are fair, each outcome is equally likely. Each outcome has probability 1 in 36. So there's a 1 in 36 chance you roll snake eyes. There's a 1 in 36 chance you roll a 5 and a 3, right? A 5 on the red dice and a 3 on the green one. Probability rules. Any probability is a number between 0 and 1. Any proportion is a number between 0 and 1. So any probability is also a number between 0 and 1. All possible outcomes together have a probability 1 because some outcome must occur on every trial. The sum of the probabilities for all possible outcomes must be exactly 1. If two events have no outcomes in common, the probability of one or the other occurs is the sum of their individual probabilities. The probability that an event does not occur is 1 minus the probability that the event does occur. The probability that an event occurs and the probability that it does not occur always adds to 100% or 1. And then we have our rules again, but now listed symbolically. So the probability rules in formal language, mathematical language, probability rules are: rule 1, the probability P of A, of an event A, satisfies 0 less than or equal to the probability of event A less than or equal to 1. Rule 2, if S, capital S, is the sample space in a probability model, then the probability that the sample space occurs is 1. Rule 3, two events A and B are disjoint if they have no outcomes in common, so can never occur together. For example, if a card is red and a card is black, a card can't be both red and black, so that would be disjoint. If A and B are disjoint, the probability of A or B equals the probability of A plus the probability of B. This is the addition rule for disjoint events. Rule 4 can be summarized as: for any event A, the probability that A does not occur is 1 minus the probability that A does occur. Probability rules example. First digits of numbers, first digits of numbers in legitimate financial records often follow a model known as Binford's law. Call the first digit of a randomly chosen record X. Binford's law gives this probability model for X. So call the first digit of a randomly chosen record X. Binford's law gives this probability model for X as, well, our numbers can only start with 1, 2, 3, 4, 5, 6, 7, 8, 9, right? We don't start numbers with 10. We don't have any other digits. So these are the digits that a number could possibly start with, right? Show that this is a legitimate probability model. So each probability is between 0 and 1. True, right? No, there's no negatives here. There's no probabilities that are like 1.5 or 4 or anything like that. So each probability is between 0 and 1. And if we sum up each of the probabilities, 0.301 plus 0.176 plus 0.125 plus 0.97 plus 0.79 plus 0.67 plus 0.58, no, not that one, plus 0.058 plus 0.051 plus 0.046, that all sums to 1. Step B, find the probability that the first digit for the chosen number is not 9. So if 9 is a 0.046 chance, then 1 minus 0.046 will give us the probability that it's not a 9. So the probability that you have chosen a record that does not begin with a 9 is 1 minus the probability you chose a record that did begin with a 9. So again, 1 minus 0.046, which equals 0.954. Find finite and discrete probability models. One way to assign probabilities to events is to assign a probability to every individual outcome. Then add these probabilities to find the probability of an event. This idea works well when there are only a finite number of outcomes. And remember, finite means fixed and limited. So a limited number of outcomes. A finite probability model. A probability model with a finite sample space is called finite. To assign probabilities in a finite model, list the probabilities of all the individual outcomes. These probabilities must be numbers between 0 and 1 that add to exactly 1. The probability of any event is the sum of the probabilities of the outcome making up the event. Discrete. Discrete probability models include finite models as well as sample spaces that are infinite and equivalent to the set of all positive integers. The Binford's law probability model was finite. So discrete covers both finite models and whole number type information, right? So equivalent to the set of all positive integers. Those are like whole numbers. Suppose we want to choose a number at random between 0 and 1, allowing any number between 0 and 1 as the outcome. We cannot assign probabilities to each individual value because there are an infinite interval of possible values. So if you were to choose a number between 0 and 1, 0.77 counts, but so does 0.777 and 0.77777, right? So there's an infinite amount of numbers between 0 and 1. A continuous probability model assigns probabilities as areas under a density curve. The area under the curve and above any range of values is the probability of an outcome in that range, right? So if you remember, we've been looking at normal curves as our main probability distribution. And if we had an image that was shaded between two values, A and B, then the shaded area under the curve is the probability of an outcome in that range. Example, find the probability of getting a random number that is less than or equal to 0.5 or greater than 0.08. So here they've shaded below the 0.5 and above the 0.8. And because we're talking about a number between 0 and 1, right, then we have this uniform distribution with shaded areas between 0 and 0.5, and also a shaded area between 0.8 and 1. The probability that a random number is less than 0.5 or equal to or greater than 0.8 is the probability that your random variable x is, or your observed data is less than or equal to 0.5 plus the probability that observed data is greater than 0.8. So you have a 0.5 plus a 0.2 or a 0.7 for a probability. So find the probability of getting a random number that is less than or equal to 0.5 or greater than 0.8. You have a 0.7 probability of getting a random number in that range. Normal probability models. We can use any density curve to assign probabilities. The density curves that are most familiar to us are the normal curves. Normal distributions are continuous probability models as well as descriptions of data. For example, if we look at the height of all young women, we find that they closely follow the normal distribution with mean mu 64.3 inches and standard deviation sigma 2.7 inches. Call her height x. If we repeat the random choice very many times, the distribution of values of x is the same normal distribution that describes the heights of all women. Like all continuous probability models, the normal assigns probability 0 to every likely outcome. The technique for finding such probabilities is found in Chapter 3. Random variable. A random variable is a variable whose value is a numerical outcome of a random phenomenon. So we're just looking at a numerical outcome of a random phenomenon. The probability distribution of a random variable x tells us what values x can take and how to assign probabilities to those values. Random variables that have a finite list of possible outcomes are called discrete. Random variables that can take on any value in an interval with probabilities given as area under a density curve are called continuous. Personal probability. A personal probability of an outcome is a number between 0 and 1 that expresses an individual's judgment on how likely the outcome is. To be legitimate, must obey rules 1 through 4 of probability. May not match another individual's personal probability of an event. So personal probabilities, to be legitimate, have to follow the same exact rules, but they're just actually an individual's judgment of how likely an outcome is. So interesting.